Good morning to all the participants and my colleagues. Thank you very much for attending the 17th class. Thank you so much for providing me this opportunity. Now, we are discussing about the bending moment and shear force diagrams. Now, this is the 6th class I am handling the bending regarding bending moment and shear force diagrams. Now, in the previous class, we have discussed so many things related to this topic, that is bending moment, shear force, the maximum bending moment, then maximum bending, positive bending moment, negative bending moment, then clockwise moment, anti-clockwise moment, then reactions, how to find out the reaction and how to plot the bending moment and shear force diagram for various beams, like cantilever beam and simply supported beams. Now in the cantilever beams, for various types, various kinds of loads, like point loads, and then point loads and uniformly distributed loads for the cantilever beams. And also we have discussed the different types of loads and different positions of the simply supported beams, again with concentrated loads and uniformly distributed load. Now I request you to go through the previous, that is classes, which is available in our DD studio. You kindly go through that. Now I will refresh the previous class, whatever the things we have discussed for 10 minutes, and I will continue with the third type of the beams, that is overhanging beams. Already we have discussed about the simply supported beam. I will give one example, that is only I am recalling it, and again simply supported beam, I will recall it again, and I will continue this class with overhanging beams. But therefore, let us go fast with the a few fundamentals related to, that is types of beams. We have discussed about this number of times. We have discussed number of times. Now kindly go through in detail. Kindly go through the previous classes. So there elaborately I have discussed about these things, and these are the types of beams. Now your live example, I have taken the photograph from the side, and this explains the bending moment and the types of beams. Now types of beams, and similarly on the continuation of the types of beams, please go through the previous class. And also we have discussed number of times about this types of loading, that is simple point load, then uniformly distributed load, and varying load and moving load, like we have discussed about this. And also the most important thing, that is conditions of equilibrium. Sigma V is equal to algebraic sum of all the vertical forces must be equal to 0 in a system, and then algebraic sum of all the horizontal forces must be equal to 0, and algebraic sum of all the moments in the loaded beam is equal to 0. Now this we have discussed how to calculate the reaction, that is one is support, the other three are point loads acting on a cantilever beam. How to calculate this we have discussed in the previous class. Please kindly go through this. Now there is only, please go back. Now there is only one support here. There are 3 point loads. The entire load is resisted by taken by the only one support, this cantilever beam. Then also it is we have discussed about this. This is the reaction, to find the reactions of the simply supported beam loaded with 2 point loads. And please go through this and refer for the more number of explanations in the previous classes. And this is one conversion of UDL into point loads. Now in this diagram, the entire UDL is converted into point load, WL kilonewton. Whereas here I have converted this entire UDL into 2 point loads. That is, total load is WL and 2 point load. It is acting at the center of the span. Half of the load, that is half UDL, it is converted into point load. Half UDL converted into point load. Total load is WL, Therefore, this is one point load which is acting at the center of the slab. And similarly, at the center of the so I have converted into 2-point loads, whereas here I have converted this into 4-point loads. WL by 4, WL by 4, WL by 4, WL. Now that is I have divided the beam into 4 parts. The 4 parts in this part, now the load UDL in this part is acting at the center. It is WL by 4. So like now we can calculate, we can convert the UDL into number of point loads for the purpose of computation. And shear force, shear force algebraic from all the vertical forces in a loaded beam, either to the left section or to the right section with shear force. Now, for example, if you consider the right section, there is one reaction and there is a W load is acting. Now, the sum of these two, one is upward, the other is downward. That is the result of this is the shear force. Now, if you get the left hand, if you consider the left hand side, if you get upward shear force, it is positive. If you get if you consider the right section, if you get the downward force, it is positive. And similarly, vice versa, we will get the result. In any section, we can calculate the shear force. And similarly, the bending moment, it is algebraic sum of all the moments at any section of the beam, along the beam, at any section, either to the either to the left hand side or to the right hand side of the beam. So that is the bending moment. Bending moment is nothing but it is a moment, bending moment. Bending moment of a loaded beam in any section we can calculate. Now, if when the beam is loaded, if the deflection must occur in this direction only. Now, this I have taken as positive bending moment, and the reverse in the opposite side, this I have taken as negative bending moment. That is, it is called sagging bending moment. Now, for this type of loading and this type of deflection, this is the bending moment occurs along the beam is sagging bending moment, and that is positive. Now, whereas here it is reverse. It reverse to this sagging bending moment, it is arcing bending moment. They consider this as negative. And now for example, now I have taken one example already. We have discussed in elaborate. Now, just I am recalling this. Now, this is the load. It is simply it is a cantilever beam loaded with 4-point load, 3-point load, and 2 UDLs. So there is only one support. For this support, that is calculate the reaction. To calculate the reaction, sigma V is equal to 0. That is sigma V is equal to 0 means sum of the downward forces must be equal to sum of the upward forces. Now, therefore, that is reaction. It has only one reaction. Therefore, entire load must be resisted by this support. This is called reaction. Isn't it? Now, this reaction, total load 4 into 2, 8 kN, plus 2, 10 kN, plus 2, 12 kN, plus 4, it is 14 kN. Isn't it? 16 kN plus 2 is equal to 18 kN. The total load is taken by this reaction is 18 kN. And immediately after calculating this shear for the reaction, now we can plot the shear force diagram. So to take a reference, first draw the construction lines below the critical point. These are the critical points where the load is acting are critical points. Now, therefore, we just drop the construction lines below these critical points. Then after you take a reference. This is the zero reference. Now, with respect to the zero reference, now there is a reaction which is acting 18 kN upward. Therefore, let us go up by 18 kN. To some scale, draw this line, that is vertical line, because this reaction is acting upward. Therefore, let us go up. And then from year to year, there is a downward force, that is UDL, is acting downward. From year to year, it is total, that is 4 into 2, 8 kN force is acting downward. Therefore, let us come down by 8 kN. Therefore, when we come down by 8 kN, the rest is 10 kN. From year to year, it is 10 kN. And see here again, at this point B, 2 kN force is acting downward. Therefore, let us come down straight away by 2 kN. Now, this is the UDL, uniformly distributed load. Below this, shear force is linear variation. Isn't it? Linear variation. It is acting downward. Therefore, let us come down by the intensity. What is the total intensity of this load? 4 into 2. It is 4 into 2. Total load is 8 kilonewton. Therefore, let us come down by 8 kilonewton. And at this point, we will come down by 2 kilonewton. Draw this line 2 kilonewton. And similarly, now suppose if you calculate the shear force according to our definition, consider the right hand section. That is 2 plus 2. 2 into 2, 4. 4 plus 2. That is 6 plus 2, 8 kilonewton. See, from here to here, wherever you calculate the shear force, we will get 8 kilonewton. If we consider the right hand section, we will get 2 into 2, 4 plus 2 plus 2, 8 kilonewton. Suppose if we consider the left hand section, left hand side, 18 kilonewton is upward and 4 into 2 is 8 kilonewton plus 2 kilonewton is acting downward. These two are acting downward. Therefore, 10 kilonewton is acting downward. Therefore, left up. The result is sum of these four. If you consider this section, sum of these vertical forces is that is 10 minus, that is upward is 18 and downward is 10. So therefore, we will get 8 kilonewton. Wherever you calculate from B to C, therefore you continue this line, draw this line for 8 kilonewton. Wherever you measure this, you will get 8 kilonewton shear force. Again at this point, there is a 2 kilonewton down, isn't it? It is acting downward. Therefore, let us come down by 2 kilonewton. Then we left with, that is 6 kilonewton. From here to here it is 6 kilonewton. See, after this, now continue this line. Now continue this diagram. That is 2 into 2, 4 kilonewton is acting downward. Therefore, when 4 kilonewton is acting downward, then what we should do? Again, it is UDL. It is a downward and it is a linear variation. Therefore, let us come down by 4 kilonewton. Now we have reached the 2 kilonewton. Left with the 2 kilonewton and this is 6 kilonewton. From here to here, we have drawn this inclined line up to 2 kilonewton. Then we have come down from here to here, it is by 4 kilonewton. And again at this point, at the point D, now there is a 2 kilonewton is acting downward. Then come down and reach the 0 point. This is how we can complete this diagram. This gives you the shear force diagram for the given system of loading. And therefore, now from this, the advantage of this shear force diagram. See, straight away we can measure the shear force from at any point, wherever you want. Straight away we can. Now we are not able to calculate the shear force at all the points. It takes too much of time. Therefore, what we will do? Normally, we will calculate the shear force at critical points. These are the critical points where the load is acting. So therefore, calculate the shear force at the critical point and then draw this diagram, complete this diagram, then we can measure the shear force. Accordingly, we can create the beam. Isn't it? And similarly, again, to plot the bending moment diagram. To plot the bending moment diagram, now we know that the bending moment at the free end is equal to 0. That is MD is equal to 0. Bending moment is 0 at the free end. Now we need to calculate the bending moment here. The bending moment at this point C. Now what is going to happen here? Now let us calculate 2 multiplied by 2 meter. It is 2 multiplied by 2 meter. Plus, with respect to this point, these two forces are creating clockwise moment. Therefore, these two are sum. So therefore, moment at this point C is equal to 2 into 2 the intensity of the force and distance. Force into perpendicular distance is the moment. Therefore, 2 into 2 and plus. Now from here to here, 2 kilonewton is acting. That is therefore 2 into 2. That is 4 kilonewton is acting at the center. Now this is 2 into 2 we have written. Where this force is acting? That force is acting. This usually acting at the center. It is assumed that it is acting at the center. Now therefore 2 multiplied by 2 into 1. Now total is equal to, that is 8 kilonewton force is acting, 8 kilonewton meter moment is acting at the center. And similarly, we can calculate the bending moment at B. If we calculate the bending moment at B, again that is clockwise moment with respect to point B. Now right side section, isn't it? So therefore 2 multiplied by 4 meter, that is 2 multiplied by 4 meter. Plus that is UDL, 2 multiplied by 2 is the total load it is assumed that it is acting at the center. Therefore, from here to here, the distance is 2 plus 1, that is 3 meter. Intensity of the load is 2 into 2, 2 multiplied by 2, and distance is 2 multiplied by 3. Now, therefore, now that is the another force, second force. And we have another force, that is third force, that is 2 kilonewton. This also creates the cosmic moment. Therefore, that is 2 multiplied by 2. 2 kilonewton into distance, perpendicular distance. Therefore, this is 24 kilonewton meter is acting. So 20 kilonewton, 24 kilonewton meter is the bending moment at this point. And similarly, with respect to A, that is bending moment at A, bending moment at A is equal to, how to calculate the bending moment at A? So therefore, see, now at A, bending moment at A is equal to, it is 2 kilonewton multiplied by perpendicular distance, that is 2 into 6. And similarly, 2 kilonewton over 2 meters span, therefore 4 kilonewton is acting at the center. Therefore, from here to here, that is 5 meter. 2 plus 2 plus 1, 5 meter. That is what it is printed here. And similarly, 2 kilonewton, it is at a distance, that is 4 meter. 2 into 4 meter. And similarly, 2 kilonewton multiplied by 2 into 2, that is 2 into 2. And again, we have another UDL, that is 4 kilonewton per meter over the over a distance of 2 meter. Therefore, 4 multiplied by 2 is the load which is acting at the center. Now, 2 multiplied by 2, it is the 4 multiplied by 2 is the intensity of the load and it is acting at the center. Now, therefore, it is 4 intensity, distance is the total load multiplied by 1 meter. It is acting, it is moment, bending moment due to this force is 4 into 2 into 1 meter. Therefore, total we will get 52 kilonewton meter. And similarly, after calculating this, see, we need to plot the bending moment. We need to plot the bending moment diagram. We need to plot the bending moment diagram. Therefore, now what we should do below this? Now take a reference. This is a reference 0, and from here to here, now this we have calculated. Mark this is 8 kilonewton meter, and mark the 24 kilonewton meter, and mark 52 kilonewton meter here. Then below this UDL, the bending moment is curvilinear, that is parabolic line, and below this the bending moment diagram is a linear line, and again below this it is parabolic line. So plot this, mark this, measure this distance and mark this and complete the bending moment diagram. Complete this diagram. Now this gives you the bending moment diagram, and for this condition, according to our sign convention, that is, it is arcing bending moment. It is negative, therefore we have plotted this below the reference line. Not necessarily it is the below, and some people are saying, some textbook, somebody will take this as positive and somebody will take the vice versa as negative. And similarly, there is another simply supported beam. For this simply supported beam, again there are two simple supports, and W kilonewton is the force acting. How to calculate this? When you look at this, that is W is the total load. It is a symmetrically loaded beam. The load is loaded at the center of the span. Now, therefore, what we should do now? W by 2 is the load taken resisted by the reaction 1, and the W by 2 is the reaction taken resisted by the reaction RC. Now, therefore, total load. Now, how to plot the shear force diagram? Take a reference 0 reference. W by 2 is acting downward. Then from this 0, go by W by 2 kilonewton. Then wherever you calculate the shear force, between this we will get W by 2. If you consider the left hand section, we will get W by 2. If you consider the right hand section, W minus W by 2. Therefore, W by 2 is downward. Therefore, it is, if you consider the section, left side is upward result, therefore positive. And similarly, if you consider this, the right side is upward, therefore it is negative, vice versa, according to our same convention. Therefore, you go up by W by 2 kilonewton, then wherever you calculate this, you will get W by 2. Now, therefore, continue this W by 2 up to this point, And at this point, W kilonewton is acting downward. Let us come down. Already we are W by 2 above the reference. Now to complete to get W kilonewton is acting at this point. Therefore, we just come down by W by 2. And then if you calculate the shear force any point between B and C, we will get W by 2. Therefore, continue this line, and at this point, W kilonewton is acting upward. They go up and reach this point. Isn't it? Now that completes our shear force diagram. And similarly, now how to plot the bending moment? Plot the bending moment diagram. Now we know that the bending moment at A and bending moment at C is equal to 0. Now to calculate the bending moment at B, either you have to consider the right hand section or left hand side. Therefore, if you consider the right hand side, it is W by 2 is the load, that is the reaction, into distance L by 2. Therefore, it is WL by 4 km. Isn't it? Now, therefore, there is only one critical point, and these two are support. Bending moment is 0 here, and due to this loading, the deflection is in this form. Therefore, it is positive bending moment. It is sagging bending moment. Now, therefore, again take reference, 0 reference, then WL by 4. Mark this distance, mark this point, WL by 4, and join this line. We will get the bending moment diagram. Isn't it? Now, in this bending moment diagram, see straight away we can measure the bending moment at all the points. At every point, we can measure the bending moment. Now, this completes the bending moment diagram. That is the advantage. That is, wherever you want, we can measure the bending moment, and accordingly we can prepare the diagram. And you know, now the one point we should notice here. Now here, the shear force changes its sign at this point, positive to negative. Shear force is from positive to negative. Now, when the shear force is from positive to negative, at that point the bending moment will be maximum. Now, it is one point one should note down, that is the maximum bending moment occurs where the shear force changes its sign. That is from positive to negative or negative to positive. There the bending moment will be maximum. We will go to the next problem. So if you consider the one more simply supported beam, again, see W is the W kilonewton per meter is acting over the entire span, that is L meter span. Now for this, you know, straight away the total load on the beam is W into L. WL is the total load. W. Therefore, WL is acting downward, RA plus RB is acting upward. Now, therefore, W, these two are sum, these two are equal. Downward force must be equal to upward force. W into L is the total force acting downward, RA plus RB is the force acting upward. Isn't it? Now, to calculate the shear, the reactions, that is straight away we can recognize, we can notice that is half load will be resisted by this, and half load is resisted by the another support, isn't it? That we can calculate by taking the moment about A. Now, follow this procedure. Now we will get WL by 2, or for more details, we can refer our previous class. And you know, after calculating the reaction RA and RB, now we can plot the shear force diagram. Now to plot the shear force diagram, again that is 0, 0 reference, and then at this point WL by 2 is acting upward. WL by 2 is acting upward. Let's go up by WL by 2. Now draw this line up to here, that is up to WL by 2. Plot this to some scale, and see after doing this, after reaching this point, now let us look at the beam. Now from here to here, WL is the total load acting downward. Therefore, now it is a uniformly distributed load. Therefore, the shear force diagram is inclined downward. Now, therefore, let us come down by W. Now, from here already we are in WL by 2 upward. If you come down, now this we continue this, and here we will get WL by 2. Downward WL by 2, it is upward WL by 2. Isn't it? Now, after reaching this point, again you go ahead, you go upward, then this point will get. So this completes the shear force diagram. Now, therefore, according to our sign convention, if you calculate this, left side will get upward result, therefore it is positive, and continue this. Now this will get positive and this will get negative. Isn't it? Now this is how we can complete the shear force diagram. And see, we can measure the shear force at all the points. At any wherever you want, you can calculate. We can measure it directly. Now we have calculated the shear force only at this point and only 3 points. But whereas from this diagram, we can straight away measure this, the shear force at all the points. Isn't it? And similarly, to plot the bending moment, diagram, let us calculate the bending moment at A and at B. Bending moment at A and B is equal to 0. Bending moment at A, because it is simply supported beam, there is no moment. Bending, because there is a support, therefore 0. Isn't it? And the critical point is the center, which is the maximum force is acting. Now W into L is acting at the center. Now therefore bending moment at this point. Now let us consider the right hand section. If we consider the right hand section, WL by 2 is acting upward. Isn't it? WL by 2 is acting downward. Therefore WL by 2 multiplied by L by 2 is the distance. That is what we have written here. WL by 2 is the force. Distance is perpendicular distance. It is L by 2. Now therefore that is the moment, bending moment due to the support. And the bending moment due to this force, that is WL by 2, is the half. And where it is acting? It is acting, it is asymmetric, it is acting at the center. That means it is L by 4 distance. That is what we have written. This is the intensity of the load and this is the distance. Now this is the intensity of the load, that is anti-clockwise moment, and this is clockwise moment. Isn't it? Now therefore, now say after calculating, simplifying this, we will get WL square by 8. That is the maximum bending moment. Now therefore, you just measure this from the reference to plot the bending moment diagram. That is from reference. You measure this distance WL square by 8 and draw this, complete this diagram. Now this is UDL. When it is UDL, below the UDL, bending moment is a parabolic line. It is a parabolic line. Now this completes. This is not the bending moment diagram. And now here, due to this kind of loading, this type of loading, the beam should deflect in this parameter, in this wave only. Therefore, it is sagging bending moment. Now this sagging bending moment is a positive bending moment. We have considered it is according to our sign convention. Not necessarily it is positive. Somebody will consider this as negative. Now we have considered this as positive, and there is no hard and fast rule. You can consider this. Somebody will consider this as negative. Now the other way, when you consider this negative, then the another moment is negative, positive bending moment. Now in our case, it is positive bending moment, isn't it? Now because it is a sagging. Now deflection is in this direction, downward direction, and this is the sagging. Now this sagging bending moment we are considered as positive bending moment. Okay. Now we'll go to the next problem. Now similarly, now you go through this. Now we have solved this problem. Now in the previous class, we just go through this. Now that is calculate the reaction RA and RE. After calculating the reaction RA and RE. Now for the given loading, now take a reference 0 reference. Now below this diagram, 0 reference. Now here 3.5 kN is acting upward. We just go by 3.5 kN. Draw this line, shear force line, and then from here to here there is a 2 kN force is acting downward. Therefore, come down by 2.2 kN. It is 1 into 2 meter. That is the total force is total UDL is 2 kN. Therefore, come down by 2 kN. Then there will be left with 1.5 kN. Wherever you calculate from B to C, by considering either right hand section or left hand section, we will get 1.5 kN at all the points between B and C. Now at this point, there is a 4 kN is acting downward. Therefore, it is already we are 1.5 above. So just come down from here to here. It is 4 kN. Now above 1.5 kN and below 2.5 kN. Therefore, this line, complete full line, is 4 kN. Now see then at this point, when you in between this, between C and D, now the shear force is 5.5 is up, 3 down. Therefore, 2.5 is the shear force, isn't it? Between this and this. between this and this. Therefore, now draw this line continuously, and when you reach this point, 3 kilonewton is acting downward. Already we are 2.5, then go down by 3 more kilonewton, then we reach 5.5 kilonewton. Now, wherever you calculate between D and E, the shear force in the right hand side or left hand side, that is 5.5 kilonewton is out. Therefore, draw this line and go reach this point. Now, this completes the shear force diagram. And similarly, calculate the bending moment at all the critical points. Now, that is shown here. Now, when you consider the right hand side, you will get at B, moment at B. One example I have given here. At B, if you consider the right hand side, we will get 5 kilonewton. If you consider the left hand side, we will get 5 kilonewton meter. Isn't it? Now, calculate this and take a reference 0, and below this UDL, it is a parabolic line. Now, this is from here to here it is 5 kilonewton, from here to here it is 8 kilonewton, and from here to here it is 5.5 kilonewton. Isn't it? Now, now complete this. It is a parabolic line, and from here to here it is straight line, and linear variation. Now, from here it is linear variation, from here to here it is linear variation. Now, this completes the bending moment diagram. Now, when you look at these two bending moment diagrams, shear force and bending moment diagram, see just below this. Now, where the shear force changes its sign, positive to negative. Now, just below that we have that is maximum bending moment. Isn't it? It is 8 kilonewton. Okay. Then we will go to the next step. Then see, we know so far we have not come across with this beams. Now it is overhanging beams. Now I request our students, I suggest our students, first read the problem very carefully. First we have to read the problem very carefully. You have to read, and then construct this diagram. If you read this carefully and construct this, most of the problems are solved. Many of the problems are, you know how to plot, you know how to calculate the reaction, you know how to plot the bending moment diagram, you know how to plot the shear force, you know how to calculate the shear force, and you know how to calculate the bending moment. You know everything, but you don't know how to plot this. When you don't plot, if you are not plotting this properly, then our problem gets wrong. Isn't it? Therefore, be careful. Read the problem number of times. More 2-3 times you must read and understand the problem. Then you must understand very clearly that is overhanging beam. This is the overhanging beam. Overhanging beam. That is overhanging beam. Now see, a beam 5 meter long has one support at the left end. One support at the left end. The other support 4 meter away. 4 meter away. Other support is 4 meter away. And with a overhanging of 1 meter to the right. It carries a point load of 6 kilonewton at the free end. This is the free end. 6 kilonewton. In addition, there are 2 point loads of 10 kilonewton and 12 kilonewton. 10 kilonewton and 12 kilonewton at a distance of 1 meter and 3 meter from the left hand support. Now, from here to here it is 1 meter, and from here to here it is 3 meter. Now, very carefully you have to read this. Then, see, after doing this, now let us calculate the reaction. First stage. Don't mix the calculations of the reaction, shear force, bending moment. Isn't it? Now, here in this case, there are the few more steps. Not that we will discuss one by one. Isn't it? Now here RA is the reaction, RD is the another reaction. There are two reactions and there are 3 point loads. 1, 2, 3 point loads. Isn't it? See, now that upward force, that is sigma V is equal to 0. Conditions of equilibrium. In the conditions of equilibrium, sigma V is equal to 0. Sigma V is equal to 0 means sum of upward is equal to sum of downwards. That is the conditions of equilibrium. It has to satisfy. Isn't it? Therefore, RA plus RD is equal to, that is 6 kilonewton down, 12 kilonewton down, and 10 kilonewton downward. Isn't it? Therefore, RA plus RD, sum of RA plus RD is equal to sum of the downward forces. It is 28 kilonewton. Now, let us calculate the force resisted by reaction, resisted load, this entire load that shared by this reaction and this reaction. Now we have to calculate that. Now we are calling this as reaction. To calculate the reaction, see now, now this is one equation we have already, Ra plus Rd is equal to 28 kN. There is one equation, two unknowns. There are one equation and two unknowns. Therefore, now we will call the one more equation, that is sigma h is equal to 0. If we call the sigma h is equal to 0, it is not relevant to this loading, this type of loading. Because no horizontal forces are acting. Now therefore, we will call the third condition of equilibrium sigma m is equal to 0. Sigma m is equal to 0. For that condition, now let us now consider the sigma m is equal to 0 and taking moment about A. Taking moment about A, now that is sum of clockwise moment is equal to sum of anti-clockwise moment. Isn't it? Now here this force creating with respect to this A, now we are considering the moment, say moment at about A, that is 10 into, that is 1/4 clockwise moment, another force clockwise moment, and another force clockwise moment. There are three more forces creating clockwise moments. And this is the another one, that is the third, the reaction which creates anti-clockwise moment with respect to this. Isn't it? Now therefore, taking moment about A, now this is Rd multiplied by distance. Rd multiplied by distance is 4 meters. 2 plus 1 plus 1. Isn't it? Therefore, Rd multiplied by 4 meters is equal to with respect to this. Isn't it? 6 multiplied by 5 meter. 6 multiplied by 5 meter. Plus, because it creates clockwise. This also creates clockwise. Therefore, 6 multiplied by 5. Isn't it? Plus 12 multiplied by 3. 12 multiplied by 3. Plus 10 multiplied by 1. 10 multiplied by 1. Isn't it? Now, this creates anti-clockwise moment. These are creating clockwise moment. That is equal to with respect to A. Now, this, if we simplify this, we will get Rd is equal to 19 kN. Rd is equal to 19 kN. We are going to get it. Isn't it? After simplifying, calculating this, simplifying this. Now, when you get Rd is equal to 19 kN, we know this Ra plus Rd is equal to so much. Isn't it? Now, substitute this value here, that is Rd is equal to 19, then Re will get 19. Now, that is the first stage. That is the first stage. Calculate the reaction 1 and 2. That is Ra plus Rd. Isn't it? See, after calculating the Ra and Rd, what is the next stage? What is the next step? The second step. The second step is that is calculating the shear force. Isn't it? Therefore, what we should do now? Take a reference. We take one reference. That is the reference. Zero reference. Now, with respect to zero reference, now we go according with the acting load how the loads are acting, how the reaction is acting. Isn't it? Now, therefore, Ra with respect to 0, Ra is acting upward. Then what we should do? We will go upward. Isn't it? And you know, from here to here, from in between this, according to the definition, calculate the left hand side. 9 kN is upward. It is a positive shear force. If we consider the right hand side, we will get 9 kN downward. Now, therefore, now between this and this, wherever you calculate, you will get 9 kN. Therefore, you continue this line. Isn't it? At this point, there is a 10 kN force is acting downward. Therefore, let us come down by 10 kN. Already we are 9 kN above. Let's come down by 10 kN. Isn't it? When you reach 9 kN, 10 kN here, then see again, let us calculate the shear force at this point. Isn't it? Between B and C. When you are, according to the definition, either consider the right hand side forces, or left hand side. If you consider the left hand side, 10 is acting down, 9 is acting up. Therefore, result is downward. Isn't it? 1 kN. Therefore, it is 1 kN. Therefore, continue this. Now, from here to here, wherever we calculate the shear force, if we consider the right hand side, if we consider, now 19 is acting upward and 18 is acting downward. Therefore, result is 1 kN up. Therefore, it is negative shear force. Isn't it? Now from here to here, see, continue the shear force line, and when you reach this point, now there are 12 kilonewton is acting down. Therefore, already we are 1 kilonewton here, come down by 12 more, isn't it? Then you reach 13 kilonewton force. And you know, if you calculate the shear force between this and this, between C and D, anywhere in the beam, if you consider the right section, 19 is up and 6 down. Therefore, result is 3 kilonewton, isn't it? 13 kilonewton. The upward is 19, downward is 6. Therefore, the result, the net force is upward. That is upward to 13 kilonewton. Therefore, from here to here, wherever you calculate, you will get 13 kilonewton shear force. Then continue this. Continue this. Then when you reach this point D, then you go up by 19 kilonewton is acting upward here. 19 kilonewton force. Then you go up by 19 kilonewton. Already we are 13 kilonewton below. Now therefore continue this. The 6 kilonewton is above. When you reach the third, now from here to here it is 19 kilonewton. This is RD is equal to 19 kilonewton. From here to here it is 19 kilonewton. Isn't it? When you reach this point, then let us calculate the shear force between D and E. Now see, if you consider the right side down, if you consider the left side, again you will get 6 kilonewton upward. Isn't it? Now therefore, now from here to here, D and E. Now from D and E, at all the points you will get 6 kilonewton. Now continue this 6 kilonewton force, and when you reach this point, there is 6 kilonewton is acting downward. Isn't it? They come down by 6 kilonewton, reach the 0 point. Now complete this shear force diagram. Isn't it? Now according to our sign convention, now this is above, that is left up. It is positive. Now if you calculate here, that you will get left down, 10 down, 9 upward. Therefore net is 1 kilonewton is acting downward. Therefore it is negative. This is full negative. Up to here it is negative. And when you reach this, now this side, see, if you consider the right hand section, right to down side and the left upside, now therefore it is positive shear force. This completes the shear force diagram. Isn't it? Okay, please proceed. Yeah. See, after doing this, see that first stage is, second stage is over. First stage we have calculated the reaction. The second stage we have plotted the shear force diagram. Please go back. See, after plotting this, straight away we can write down. See, after plotting this, straight away we can write down. This is positive shear, this is positive shear, and this is the negative shear force. Isn't it? Therefore, the maximum shear force in this beam is, there are two maximum shear forces. One is positive shear force, 9 kilonewton. The other one is 13 kilonewton is the negative shear force. Isn't it? That we have to mention. See here, now we have to write down this, that is shear force at E is equal to 6 kilonewton. Shear force at D is equal to, at D, this is D. Now see, 6 kilonewton positive, 6 kilonewton positive. And at D, that is 13 kilonewton negative, 13 kilonewton negative shear force. Now see, we have to design for both, isn't it? Here, isn't it? We have to design for both, our beam will be safe. And you know, if you come this here, now at this point, the shear force, that is 13 kilonewton negative shear force and 1 kilonewton shear force. Therefore, 13 is maximum. Now we need to design this for, this section to be designed for 13 kilonewton shear force. When you reach this point, see, 1 kilonewton minus, that is negative shear force, isn't it? 9 kilonewton is positive shear force, isn't it? When you reach this point, it is 9 kilonewton positive shear force, isn't it? Now, therefore, you have to mention there are two maximum shear forces. One is positive shear force, 9 kilonewton. The other one is 13 kilonewton negative shear force. That you have to mention in the result. Okay, please next. Okay. Then, see, after doing this, now let us plot the shear force diagram, bending moment diagram. Now, this we have completed this, the plotting the shear force diagram. Now, let us plot the bending moment diagram. To plot the bending moment diagram, that is the third step. See, we know that the bending moment at the simply supported area is equal to 0. Bending moment at A is equal to 0. Bending moment at B is equal to 0. Isn't it? and the bending moment at D is equal to bending moment at D is equal to bending moment at D is equal to, that is right side. Consider the right hand section, right side. If you consider the right section, 6 multiplied by 1, it is 6 kilometer. 6 multiplied by 1 is the 6 kilometer meter with the bending moment at this point. When you come to this point, when you reach to this point, the bending moment at C is equal to bending moment at C is equal to, see, now this is from here to here it is. It is 6 kilometer multiplied by 2 meter. 6 kilometer multiplied by 2 meter. The other one is the reaction. 19 kilonewton into 1 meter. 19 kilonewton into 1 meter. See, one I have taken positive, the other one I have taken negative, isn't it? Now here, the one is positive because it creates clockwise with respect to this point. This creates anti-clockwise, therefore with respect to this, with respect to one is positive, the other one is negative, isn't it? And you know, we'll get the result, it is 7 kilonewton meter. 7 kilonewton meter is the bending moment at this point. If you consider the left section, if you consider the left hand side, see now, this creates the clockwise and this creates the anti-clockwise. Therefore, 9 multiplied by 3 meter. 9 multiplied by 3 meter. Isn't it? And with respect to C, bending moment at C is equal to, by considering the left hand section, this is 9 into 3 meter. And the other force, it creates anti-clockwise 10 into 2 meter. 10 into 2 meter. That is what we have written here. Therefore, the result is 7 kilonewton meter. Therefore, if you calculate this bending moment by considering either right hand section or left hand section, we will get the same result in both the cases, isn't it? Now, similarly, if you calculate the bending moment at this point, at B, very simple. See, now let us consider the left hand side. We will make more simple because we will reduce the burden, that is calculation burden. Therefore, it is 9 kilonewton, 9 into 1 meter, 9 into 1 meter. It is a 9 kilonewton meter with the bending moment at B. If you consider the left hand section. If you consider the right hand section, what is going to happen? Let us see. Now this is 6 multiplied by 4 is the shear force clockwise, isn't it? 6 multiplied by 4 with respect to B, and 12 multiplied by 2, it is clockwise, that is 12 multiplied by 2, and then this creates anti-clockwise moment. Therefore, 19 multiplied by 3, 19 multiplied by 3, then we'll get the 9 kilonewton meter. Now, if you consider in the right hand section or left hand section, we are going to get the same result, isn't it? Now, at this point, MA is equal to 0. It is better always to follow some, that is disciplined way. You have to compute the disciplined way. Either you go from this side, like this, from here to here, isn't it? Or first calculate the reaction. Bending moment at 0, bending moment at D, bending moment at C, bending moment at B, and bending moment at, that is what we have followed this here, isn't it? Either you can consider the right hand section or left hand section. Okay. Now, after doing this, for this type of loading, it is expected. It is obvious the beam will deflect in this shape, isn't it? Definitely, it should deflect in this form only. Therefore, it is here sagging. Here it is hugging. Therefore, it is sagging bending moment. Here it is hugging bending moment, isn't it? Therefore, it is positive bending moment. Here, negative bending moment, isn't it? You must take care of these things, isn't it? Therefore, these two are hugging bending moment, sagging bending moment, and this is hugging bending moment, isn't it? Negative bending moment. Therefore, see, now take a reference 0. Take a reference 0. After taking this reference, we have calculated here the bending moment. Now from here to here, see, you have to mark, that is this point. If you 9 kilonewton meter at B, now to subscale, mark this point, isn't it? Measure the distance and mark this point. It is 9 kilonewton meter. And similarly, at this point, it is 7 kilonewton meter. Measure this distance and mark this point. And likewise, at D, it is a downward, isn't it? Sorry, it is a arcing bending moment below the reference. It is negative bending moment, 6 kilonewton meter. Now, join all these points from 0 to 9 kilonewton meter and 9 kilometer to 7 kilonewton meter, and from there to here, and from here to this 0. Now, that gives you the bending moment diagram. This is the shape of the bending moment diagram. Now, this hatching is only to know the shape of the bending moment diagram. And from this, now we can measure the bending moment at all the points. We can measure the bending moment at all the points there straight away, isn't it? That completes the bending moment, plotting the bending moment diagram for the given for the given beam. The most important thing here you should remember here. See, number one. See here, the shear force changes its sign from positive to negative, where the bending moment is maximum. Where the bending moment is maximum here, isn't it? Bending moment is maximum. And here again, at this point, the shear force changes from negative to positive. From negative to positive. There again, the bending moment is maximum at this point. And here also we have to mention, that is bending moment. What is the maximum bending moment? Now, maximum bending moment is positive 9 kilonewton meter and negative 6 kilonewton meter. We have to mention like this. Now we will come across with one more problem in this here in the bending moment diagram. The one more problem come across with, there is a zero bending moment at this point. The zero bending moment, the bending moment is zero at this point, isn't it? Now, because the bending moment changes its sign from positive to negative. The bending moment is zero at this point, isn't it? Bending moment is zero at this point, and this point is called point of contraflexure. This is the point where the bending moment is zero and the shear force and the bending moment changes its sign from positive to negative or negative to positive. The point of contraflexure is the point where the bending moment changes its sign and it is zero, isn't it? Now that point is called point of contraflexure, isn't it? Now there is a job. Now we need to find out where it is located. Now where this bending moment, this bending moment is zero, or where the point of contraflexure is occurs available, isn't it? Therefore, what I should do, now let me mark, that is YY at that point. Now it is the section YY. The bending moment is zero at Y. We don't know where exactly, therefore we need to find out where the bending moment is zero, isn't it? The bending moment diagram shows it is a zero bending moment at this point, isn't it? The bending moment changes its sign. Okay. Then if you look at this, bending moment is zero. Now this we have considered, this is Y. Now see, straight away let us go to the beam, isn't it? A loaded beam. We'll look at this. This we have considered, we have taken this as YY. Y section YY. At Y section, the bending moment is zero, isn't it? Where it is located, that section is located at a distance Y from the right hand support, from this support, from D. From D, it is at a distance Y. The bending moment is zero, or the bending moment changes its sign, or the point of contraflexure occurs at a distance Y from the right hand support D. Now that is our problem. Now we need to find out. How to find out this? Now to find out this, now what we should do, now already we have marked, it is at section YY, at a distance Y from D, the bending moment is equal to zero. See? Now therefore, when you look at the bending moment diagram, from the bending moment diagram at YY, bending moment at YY is equal to zero. Now therefore, let us calculate the bending moment at this point. Let us calculate the bending moment. To calculate the bending moment, 6 multiplied by 1 plus y. 6 multiplied by 1 plus y is the bending moment from the beam, from this diagram. If you calculate the bending moment at this point, 6 multiplied by 1 plus y. That is, isn't it? This is clockwise bending moment, and this creates negative anti-clockwise bending moment. Therefore, 19 into y. 19 into y. Bending moment at this point, 6 multiplied by 1 plus y minus 19 into y. This is what we have done. and that is equal to 0. See, the bending moment is 0 at that point. That is equal to 0. Isn't it? When you solve this equation, we will get y is equal to, that is distance y. Now from here to here, the distance is 0.46 meters. Isn't it? The bending point of contraflexure occurs at a distance 0.46 meter from the right hand support. Isn't it? Now we have to mention, now in this problem, suppose if you get this problem in your examination, now you must write down, or you must write the answers. Number 1, the first one, positive shear force 9 kilonewton, negative shear force, maximum positive shear force 9 kilonewton, maximum negative shear force 13 kilonewton, maximum positive bending moment 9 kilonewton, maximum negative bending moment is 6 kilonewton, and the point of contraflexure occurs at a distance that is 0.46 meter from the right hand support. Now this completes the preparation of bending moment and shear force diagram from the given loading. Isn't it? Now we'll have one more problem. Let us solve one more problem. Isn't it? Like, again, we must read very carefully the problem. Very carefully you must read the problem. There is a UDL acting over the beam. That is 6 meter span. It is 6 meter span. 2 kilonewton per meter is acting over the span. Isn't it? There are two supports at A and B. The reaction A and reaction B. Reaction A and reaction B. Now, the beam length is, total beam length is 6 meter and 2 meter is cantilever and 4 meter is in the supported portion. Isn't it? It is the cantilever portion. Cantilever portion is overhanging portion. That is B to C, the overhanging portion. Therefore, we know that in the similar manner, the first stage always find out the reaction A and reaction B. Therefore, sum of the upward forces must be equal to sum of the downward force. Sum of the downward force, total downward force is 2 multiplied by 6 meter. 2 multiplied by 6 meter, it is 2 multiplied by 6, which is equal to 12 kilonewton. RA plus RB, RA plus RB is equal to 12 kilonewton is acting downward. Now, that is we have one equation, two unknowns, RA plus RB is equal to 12 kilonewton in one equation, two unknowns, isn't it? Therefore, now let us take the third conditions of equilibrium, isn't it? Sigma ME is equal to 0. Sigma ME is equal to 0. That is taking moment about A. Now what is going to happen? Now this force creates clockwise moment and this reaction creates anti-clockwise moment. Therefore, moment of all this force about this point A is equal to 0. Now therefore, 2 multiplied by 6. 2 multiplied by 6, where it is acting at the center, at 3 meter. Therefore, it is 2 multiplied by 6 acting at the distance 3 meters is equal to RB into 4 meter. RB into 4 meter. Doesn't matter. Now this is how we can calculate that is reaction. Now therefore, RB will get 9 kilonewton force. RB. Now when you get RB is equal to 9 kilonewton, we know the total force. Isn't it? 12 minus 9 will give the RE is equal to 3 kilonewton. It's a very simple procedure we should follow. Okay? Then next slide please. Then after this, after calculating this, so after calculating the reaction, after calculating the reaction, RA is equal to 3 kilonewton, RB is equal to 9 kilonewton. Now let us plot the shear force diagram. To plot the shear force diagram, that is, draw the reference line, 0 reference line. You take this reference, and at this point RA, reaction RA is acting upward. 3 kilonewton is acting upward. Let us go up by 3 kilonewton. Draw this line, 3 kilonewton, isn't it? And from here to here, 4 into 2, that is 8 kilonewton force is acting downward. Now we have gone up by 3 kilonewton. Now let us come down by 8 kilonewton. From here to here it is 8 kilonewton. Already we are above the reference 3 kilonewton. Now let us come down by 5 kilonewton. Therefore, from here to here, we have come down by 8 kilonewton. Isn't it? The 8 kilonewton. When you reach this point, at B, that is 9 kilonewton, reaction is acting upward. Therefore, from here, we will go up by 9 kilonewton. See, already we are below 5 kilonewton and above, let's go by 4 kilonewton. Therefore, this is 9 kilonewton is acting upward reaction. And from year to year, there is a 2 into 2, 4 kilonewton is acting downward. This is the 4 acting downward. Therefore, from year to year, draw the inclined line. Now, that we reach this point. This is 0. Now, complete this diagram. Now, this is reference 0, then 3 kilonewton, then 8 kilonewton, then 9 kilonewton, then 0. This is 4 kilonewton, 0. Isn't it? Now, this completes the shear force diagram. Again, now left up shear is positive, isn't it? And here, when negative. Now, here again, left, right down, right up, right down is positive, left up is positive. Therefore, positive shear force diagram. And also, you must remember, you must note down here. Now, here, the shear force changes its sign from positive to negative. Shear force changes its sign from positive to negative, and here negative to positive. Therefore, below this, that is where the shear force changes its sign. That is zero shear force, zero shear force. Now, this is the where the bending moment is maximum. Isn't it? The bending moment is maximum at this point. Isn't it? And bending moment. And similarly, here, the shear force changes from negative to positive. Therefore, the maximum bending moment. This is the maximum bending moment. Below where the bending shear force changes its sign. So therefore, now let us when we don't know where this is, this point, where it is this point, we don't know the location of this, the shear force 0, that is where the shear force changes sign. The 0 shear force changing the sign from positive to negative. Now we don't know where exactly it is located. Therefore, what we should do, now we will consider this as XX, or section XX. Section XX, the shear force is 0, isn't it? At a distance x from the support B. Now, therefore, first let us find out the x. X is how much? Isn't it? What is the distance? Where it is 0. Now, therefore, this we have to recognize this. Now, to calculate the shear force, calculate the shear force at XX, section XX. At section XX, at a distance x from B. Now, let us calculate the shear force, isn't it? Because from shear force diagram, Fx, that is shear force at xx is equal to 0. Now let us calculate it. Now this is, isn't it? Now if we consider this, now see, now from here to here, it is 2 plus x. That is the force, shear force, 2 kilonewton. 2 kilonewton force over this time multiplied by distance. Multiplied by 2 plus x, isn't it? That is downward. The other force is acting upward. Now it is 9 kilonewton. Therefore, x is equal to 2.5 meter. Therefore, the shear force changes its sign at a distance 2.5 meter from the right hand support. Isn't it? Or this point. Therefore, we know that at this point, the bending moment is maximum. The bending moment is maximum. Therefore, now let us calculate the bending moment at this point. Isn't it? To calculate the bending moment at all these points. Now, therefore, at all the points, critical points, MC is equal to 0, MB is equal to 2 multiplied by 2. 2 multiplied by 2 is the load. It is acting at a distance, that is distance half of the distance, that is 2 multiplied by 2 at a distance 1. Therefore, the shear force bending moment is 4 kilonewton meter. And similarly, at XX, at MXX, bending moment, maximum bending moment at this point. Therefore, either we can consider this side or we can consider this side. Now, if we consider the left hand side, the 3 multiplied by 1.5 meter, because it is 2.5 meter, therefore it is 1.5 meter. 3 into 1.5, it is 4.5 meter. Now, this is 1.5 into 2 at a distance 1. That is 0. That is half of this distance, 1.5, 0.75. Isn't it? It is 1.5 meter. Therefore, load into distance is the intensity of the load, it is acting at the center. It is 0.75 meter. Therefore, 3 into 1.5 minus 2 into 1.5 into 0.75 will get 2.25 kilonewton meter. This is the maximum bending moment. Now, therefore, see, for this loading, the bending should be in this shape only, isn't it? Now, only in rare cases, there are only rare cases there are possibility it may come hugging throughout. That we need to address. Now, later stage we can address it. Now, whereas here, no, it is negative. It is a positive bending moment, sagging bending moment. It is hugging bending moment, isn't it? Therefore, hugging this is the sagging bending moment positive. Let us go up by 2.25 meter, just below this 2.25 kilonewton meter, and already we have calculated the shear bending moment at this point. It is 4 kilonewton, and this is negative hugging bending moment. Now below this plot. So this is the curve. This is the parabolic line. Now we will continue this from zero reference to. Now this is the parabolic line. Now this is 6. It is 2.25 kilonewton meter. This is 4 kilonewton. Therefore, you continue this line. Now draw this parabolic line, and from there you go and reach this 0 point. Now this gives you the bending moment diagram. Isn't it? This is the bending moment diagram. And there is again we need to address. We need to calculate the bending, the point of contraflexure. Again we have here. See when the shear force changes its sign from positive to negative or negative to positive, the bending moment will be maximum. Where the bending moment changes its sign from positive to negative, there the point of contraflexure is available. Isn't it? Now we need to address this. Again, we have to calculate this. Now, therefore, to calculate we don't know where exactly it changes its sign. The bending moment changes its sign. We don't know. Therefore, now let us take this as y section. It is the y section. At a distance y from the free end C. At a distance y. Now let us calculate the bending moment at y and equal it to 0. Now that is what we have done. When we do this, bending moment at y is equal to, that is 2 into y. Where it is acting 2 into y is the intensity of the load. That is this distance 2 into y. Where it is acting at a distance y by 2. This is y by 2. Half of it is assumed that this entire load is acting at the center. Isn't it? At the center. Therefore, it is y by 2. Minus, this is 9. This distance is y minus 2. Y minus 2 is the distance. This is the distance. This is what we have written. Isn't it? Now, after simplifying this, we will get 2 answers for y. Y is equal to 2 answers. Simplifying this, isn't it? This equation. After simplifying this equation, we will get y is equal to 6 meter and 3 meter. Isn't it? Now we will get 2 answers. Now y is equal to 3 meter. We will take this y. Now from here to here it is 3 meter. From here to here it is, because we can't take 6 meter. If you take 6 meter, it will reach y0. Isn't it? It becomes this location. Then not practical. Therefore y is equal to 3 meter. Therefore from here to here it is 3 meter. Now from this support it is 1 meter. The point of contraflexure occurs at a distance that is 1 meter from support B or 3 meter from point C. Isn't it? Now you have to write down the answers for this. Now you have to calculate the results. That is positive shear force, that is 4 kilonewton meter. Maximum positive kilonewton is 4 kilonewton. Maximum negative shear force is 5 kilonewton. And then maximum positive bending moment is 2.25 kilonewton meter. Maximum negative bending moment is 4 kilonewton meter. And the point of contraflexure occurs at a distance that is 3 meter from C. Isn't it? This completes the entire problem of the given system of load. Isn't it? Now we'll go to the next one. In the similar manner, in the similar way, now you deal with this, find out the sigma V. Sigma V is equal to 0, calculate the reaction. When you look at this beam, definitely it is possible we can straight away we can write down, not necessarily to do all these process. See, because it is symmetrically loaded. The beam is symmetrically loaded. 1 meter cantilever left side, 1 meter cantilever overhanging left side, 1 meter overhanging right side. Therefore, definitely we can understand that is these two are carrying the equal load. These two are carrying the equal load, that is 6 kilonewton and 6 kilonewton. See, when you have calculated the reaction RA and RB, we can go to the second step. We can go to the second step. Now from this, now let us take a reference 0, 0, 0 reference. Now with respect to this reference, now from here to here, that is 2 kilonewton into 1 meter distance. 2 kilonewton force acting over this AB. Therefore, let us come down by 2 kilonewton. Isn't it? Let us come down by 2 kilonewton. Now, at this point, 6 kilonewton is acting upward. Let us go up by 6 kilonewton. 2 kilonewton already we are below the reference. Let's go up by 4 kilonewton. That from here to here it is 6 kilonewton reaction. Now, from here to here, that is 2 into 4, that is 8 kilonewton is acting downward. The shear force, the force acting, load acting on this big portion is 8 kilonewton. Already we have gone up to 4 kilonewton, just come down by 8 kilonewton. Above 4 kilonewton, already, now this, we have come down by the shear force acting downward, therefore let us come down by 8 kilonewton. 4 above and 4 below. And when you reach this point, now this 6 kilonewton is acting upward. Already we are 4 kilonewton below. Let us go up by 2 more kilonewton. Isn't it? We have reached 2 kilonewton. And at this point, between this and this, 2 into 1, that is 2 kilonewton force is acting downward. Therefore, let us come down by 2 kilonewton. Isn't it? That completes the shear force diagram. Isn't it? When you look at this beam, when the shear force diagram, see here shear force changes from negative to positive. Isn't it? Therefore, the maximum bending moment is here. Now, this is the positive to negative. Therefore, the bending moment, maximum bending moment is here. Isn't it? And when it changes from negative to positive, the maximum bending moment. Isn't it? The maximum bending moment is here. Isn't it? Now, and you know that is here. So, in this case, where is the shear force changes? The shear force changes at the center because it's symmetrical load acting. If we calculate, we will get that is x is equal to 3 meters. From here to here, we will get 3 kilometers, 3 meters. Isn't it? Now, in the similar manner, what we have discussed in the previous problem, in the similar manner, we can calculate the shear force at this point equal to 0, then we get x is equal to 3 meters. Isn't it? And similarly, now we can calculate. Similarly, we can calculate the moment, bending moment. To calculate the bending moment, step 3, that is D is 0, bending moment, A bending moment 0, and at C, that is 2 into 1, 2 into 1 is the load, it is acting at the distance center. Now therefore, that is 1 by 2, that is 0.5, 1 kilonewton meter. And similarly, at this point, calculate the bending moment at xx, already we have calculated this x, that is at the center. If you calculate the center, we are going to get that is 3 kilonewton meter. Again, we will get 1 kilonewton meter. And for this condition of for this loading, the beam must deflect in this way only. Therefore, it is sagging bending moment, sagging bending moment, sagging bending moment, sagging bending moment. Therefore, see now with respect to this reference, below this, it is 1 kilonewton meter, mark this, and 1 kilonewton mark this, and 3 kilonewton meter we mark this. Isn't it? Then the entire loading is UDL. Therefore, draw the parabolic line, and join all these points. That gives you the bending moment diagram. Isn't it? Next slide, please. And you know, now this is one again. There are 2 points of contraflexure here. That is point of contraflexure, bending moment changes its sign from positive to negative, negative to positive. There are 2 points of contraflexure. We need to calculate the point of contraflexure here. Now this is where it is located. Now therefore, now in the similar way, you go upward, and from this, see this is YY, where it is at this section, bending moment is equal to 0. From the diagram, look at the diagram, bending moment diagram, bending moment is 0 at this point. Now where it is 0? At the distance y from the right hand support. Now calculate the shear force bending moment at YY section. If you calculate the bending moment at YY section, we are going to get this equation, isn't it? Now when you are going to get this, nothing, just y, 2 into y, UDL into distance y, 2 into y. Where it is acting at a distance y by 2, y by 2. So this is what we have here. The other one is, now here, the reaction, 6 kilonewton, that is y, this distance, y into, say, 6 kilonewton into this distance. Therefore, 6 into y minus 1. After simplifying, we are going to get it. Now, this is the form in this equation form. It is quadratic equation. Now, therefore, let us find out. So for this, there is a solution for the equation. Now, substitute that is A is 1 here, and B is minus 6, and C is 6. Substitute, we are going to get 4.73 meters and 1.2 meters, 1.27 meters. Now, from here it is 1.27 meter. Now, from here, the bending moment. From here it is 1.27 meter, and from here it is, that is 4.73 meter. There are 2 points of contraflexure available here. Now again you have to write down the solution. 4 kilo answers or the tabulation of results. 4 kilonewton positive shear force, 4 kilonewton negative shear force, and then 1 kilonewton negative bending moment, maximum bending moment, negative bending moment, and maximum positive bending moment 3 kilonewton meter. That is how you have to complete the procedure, plotting the bending moment and shear for that. Okay. Thank you very much for everybody. Thank you all. Thank you for your participation. Thank you so much.